Ladies and gentlemen, my name is Falkowska. I represent Białystok University of Technology in Poland, and I would like to present you the results of my cooperation with Gdańsk and Lublin Universities of Technology about optimization of the gyroid structure of a cobalt-based alloy produced by laser powder bed fusion. Porous structures are very popular in many fields, especially in reconstructive medicine, mainly due to their ability to be overgrown with bone tissue. One of such structure is the gyroid. I'm sorry. Is a gyroid structure, is a type of triple periodic minimal surface, and has a lot of advantages, mainly the structure mimicking the topological, mechanical, and physical properties of trabecular bone. What next? The mesh is based on sheets, so it is possible of creating uniform and interconnected structures that minimize stress concentration and has a good energy absorption capacity per unit mass. Such complex structure can be manufactured using additive manufacturing, and in this case it was a laser power bed fusion method. The specimens to our tests were produced from cobalt-based alloy in powder, and we created five types of specimens. 4 types, it was a gyroid structure with different relative density, and it was 80.5%, 27%, 50%, and 66%. And we also created specimens with near zero porosity, like solid material. First of all, we try to check what will be the structure after manufacturing process. For this, we use an tomographic study. It is a non-destructive method which can assess imperfections and defects which caused during manufacturing process. For this study, we use realistic geometrical structures. So it was here, and nominal shape of gyroid cell, and we want to access defects. We can see that all defects mainly are from the results of the laser power bed fusion methods, like micro notches between subsequent layers, like significant surface roughness, or balling effect, which is caused by non-sufficient melted particles. And we can see in the unit cell here, that gyroid structure has notches. Sometimes these notches are sharp, so it can cause a strong concentration of stress. Next stage was distribution of micropores in tested structures. In this stage, we saw that the dominant number of small pores in the volume up to 2,530 cubic micrometers were in this structure. Approximately, it was 33%. The highest value was for a relative density of 27% of gyroid structure, and the lower value, 30%, for 66 relative density of gyroid structure. So we saw that the largest peaks in all graphs represent pore, in very small pore. It was about 1,090 up to 1,180 cubic micrometers. Next, was the experimental study. We know that gyroid structure can be exposed to tensile and compressive loadings, but more dangerous are tensile loadings. So these specimens were conducted to monotonic tensile testing, and after this experiment, we obtained effective values of strength parameters like ultimate tensile strength, Young modulus, yield strength, and we can see that the values of strength parameters increases with relative density. For example, for 80.5% of relative density, ultimate tensile strength was 70 megapascals, and increases more than 5.5 times in the case of 66% of relative density. Obtained values of relative strength parameters can help us to estimate the optimal density of the gyroid structure. For this case, we create two relations. One of them, which was called coefficient alpha, it was a value of ultimate tensile stress of gyroid structure with material of some porosity related to value of ultimate tensile stress of the material with near zero porosity. This coefficient can be shown in this form, in this approximation. And the second one, coefficient beta, it was a relation of effective value of Young modulus of some porous materials with some relative density related to Young modulus of materials with near zero porosity. And this approximation is here. So what we can see? We can see that exponents in this approximation are different. So in the case of alpha coefficient, exponent is 1.8 and refer decrease of strength in the gyroid structure. The second coefficient exponent in the coefficient beta is 2.1 and refer the decrease of stiffness of gyroid structure. So we can't compare this rate of changing and decreasing this value, but we can estimate the optimal density of the gyroid structure. So taking account and information, for example, here, for elastic modulus for bone, we can range from 70.6 up to 21.5 gigapascals. Using a relation with coefficient beta, this value of stiffness can be referred as this range, so 0.09 up to 0.11. So in this case, we can see, tell that value of relative density will be a range from 31 up to 35%. So the next step, using relation with coefficient alpha, we can say that this value of relative density is related to value of coefficient alpha from 0.12 up to 0.15, and it is referred to value of ultimate tensile strength, which will be 122 up to 145 megapascals. So in this very simple relation, we can obtain this optimal density, which is necessary for some kind of bone, human bone, to replace it. And after experimental tests, microscopic examination were done. So we can. It is obvious that in this case, our fracture is changing and it's related to relative density. So in the case of the lower densities, the fracture plane is more perpendicular to applied load. With increasing the relative density, the applied load is try to be more parallel. What's more, we can see characteristic sharing in this case, and in lower densities we can observe characteristic grooves. So it's very characteristic for these densities. What's more, we can see about microscopic examination. In this case, we observe all imperfections, all defects, which can be caused not by geometric of gyroid structure, but laser-powered fusion methods. So in the case of cobalt-based alloys, during this process, it is very characteristic that during this process is presence of martensite. So martensite is creation. So then it is caused by, we can see boundaries between particles, we can see voids, and then also we can see a Bolling effect. So come to conclusion, we claim that during implant design, it is important to select the optimal structure with properties similar to those of bone tissue, especially in the case of elastic modulus. The voids and notches which present in the metamaterial are the result of both the specified geometry of the material's mesostructure and the manufacturing process. The technological process itself influences the presence of pores in the structure. Microscopic observation of the fractures show features characteristic of cobalt-based alloys. In addition, the presence of martensite produced by laser power bonding was found to be the main cause of the formation and development of cracks during loading. The microcracks and microcavities formed during this process, although not having a major effect for the properties determined by the uniaxial testing, but can have a significant effect on fatigue test, especially in the case of high cycle fatigue range. So the general conclusion is that before practical use of tested metamaterials, such as in implantology, we have to perform fatigue tests. So it was a part from my recent work, so if you are interested about my activities, look at my profile. So thank you for attention.